Hello students, welcome to Maths Online Academy by Sandhya. Myself Sandhya. I am very happy to welcome you all to this complete class 10th mathematics course. In this video series, I am going to teach the complete class 10th mathematics syllabus in a very easy and simple way. Even if you feel mathematics is difficult, don't worry. I will explain every concept step by step in a clear and easy method. So every student can understand easily, interestingly and confidently. In this course, I will cover all important chapters, textbook questions, board exam questions and shortcuts and easy tricks to get good marks in mathematics. So stay connected with me, learn regularly, practice daily. Let's make mathematics easy and interesting together. Let's start our math journey. In class 10th mathematics syllabus, total 14 chapters. Those names are real numbers, sets, polynomials, pair of linear equations, quadratic equations, progressions, coordinate geometry, similar triangles, tangents and secants, mensurations, trigonometry, applications of trigonometry, probability, statistics. Today I am going to teach you the very important concept, division algorithm, in chapter number 1, real numbers. I am not going to teach directly formulas. Let's discuss some interesting puzzle about bees and flowers. Let's start. First, we will solve an interesting puzzle about bees and flowers. And by the end of this video, we'll understand what is dividend, what is divisor, what is quotient, what is remainder, and the famous formula A equal to BQ plus R, and R has some condition 0 less than or equal to R less than B. But wait, if it looks difficult now, but end of this video, it will become very easy. Students, numbers are everywhere in our daily life. From the moment we wake up, we check the time, we count the money, and we measure the height and weight. So, numbers are in our daily life. Now, let us look at a very interesting puzzle. In this puzzle, we have 5 conditions. About the bees and flowers puzzle, if bees sit on 2 flowers, 1 bee is left. If bees sit on 3 flowers, 2 bees are left over. If bees sit on 4 flowers, 3 are left over. If bees sit on 5 flowers, 1, 2, 3, 4, 5, nothing is left over. So 0. No one is left over. So, and the last condition is the total number of bees are less than or equal to 50. Let's solve. What is the condition? What is the question is here means how many bees are there? That is the question. So, let's assume total number of bees equal to X. And in this 4th condition, if bees are sit on 5 flowers, nothing is left. So, X equal to 5 flowers. 5 flowers are shaded. 5 into that bees, let's we take A, 5A plus 0. And here same, X equal to how many flowers? 4. Here divisor is 4. 4 into we don't know how many bees are sitting in flowers. So this is also B. And remaining one is 3. In this condition, same, x equal to, here divisor is 3. 3 into, how many bees? We don't know. So here C plus remainder is 2. And here also same, 2 D plus 1. Here we don't know A, B, C, D. For example, bees are sit on 5 flowers. We don't know how many bees are sat on there. Here also same. That's why we are assuming those bees are A, here bees are B, here are C, here is D. And by this condition, we can get one clarity. Remainder is 0. Here less than or equal to 50. Means those number of bees may be 5 factors. So therefore let bees may be 5, 10, 15, 20, 25, 30, 35, 40, 45 and 50. Based on fourth condition and fifth condition, we can guess. By this condition that number of bees are 5 factors. And those are less than 50 or equal to 50. So maybe chances the number of bees equal to from 5 to 50. Okay. And I will rub this one. From this is the first one, this is second, and this is third, and this is fourth, and fifth one is what? Fifth one is x less than or equal to 50. Okay? By fourth and fifth conditions, we are getting little bit clarity. Those bees are maybe 5 to 50. And from first condition, x equal to 2d plus 1. 2d plus 1 means it's clearly mentioning that is odd number. From this, we can choose odd numbers. What are odd numbers from 5 to 50? 5 and 10 is even. So 5, 15, 25, 35 and 45. From first condition, we filtered from 1 to 50, 5 to 50 to 5 to 45. And that number is compulsory odd number. First condition is clearly mentioning plus 1. Plus 1 means it will become compulsory odd number. And next, from second condition, x equal to 3c plus 2. So it is divisible by 3. It is divisible by 3. It is divisible by 3 means here are 2. Remainder will come 2. So it's satisfying. 15 by 3 means 3 5s are here. Remainder is 0. So this is wrong. 25 by 3. 3 8s are 24. Here remainder is 1. So it's not satisfying. And next 35, 3 1s are 3 and remainder is 2. So this is satisfying. 5 and 35 are satisfying. And next 45, 3 1s are 3 5s are. Here remainder is 0. On condition of 2, these two only satisfying. So finally 5 and 35 are the numbers to maybe chances to total number of bees 5 and 35. And next to third condition, the remainder is 3 divisible by 4. Here remainder is 1. So this is not satisfying. Divisible by 4. Here remainder is 3. Sorry. This is satisfying. On the basis, on condition of third condition, the final answer is 35. So let's check. So from one condition to fifth condition, we are filtering all numbers from 5 to 50 to become 5 to 45. And second condition, it become 5 and 35. And third condition, the final number of bees are total number of bees equal to 35. So we get the final answer is 35. Let's verify all. Total number of bees are 35. The final answer is 35. So for 35, see here, 35 divisible by 2, 1 is 1, 7. Here remainder is 1. So this is satisfied. For 35, here divisor is 3. 3 ones are 3 ones are here, and remainder is 2. This one also satisfied. And 35 by 4. Here remainder is 3. So this one also satisfied. 35, 5. 7 remainder is 0. This one also satisfied. So final answer is 35. All conditions are satisfied. So the total number of bees are 35, and that one also less than 50. So this is the answer. Here 35 equal to 2. Here something D plus 1. This is the dividend. This is divisor, na? Divisor means that flower is sharing. Number of flowers are there? That is this one. So divising, sharing. Those flowers are sharing the bees. That is the divisor. This is the quotient. This is the remainder. So the famous formula, what? A equal to BQ plus R, and 0 less than or equal to R less than B. Here see, here A is the 35. In first condition, B is the 2. Q we find out, plus R is the 1. So 0 less than or equal to R less than, what is the B here? 2. R means here 1, na? So less than R may be 0, 1, but not equal to 2 or less than 2. Here 35 by 2. 7. Q equal to 17 here. division algorithm formula. The famous division algorithm formula A equal to BQ plus R, and R has the condition 0 less than or equal to R less than B. In division algorithm formula, clearly we discuss, for example, see one example, 35 is divided by 2, and this is dividend, this is divisor, quotient, and this is the remainder. This is remainder. So based on that, let's try. Let's see one example, this one here. Dividend equal to divisor into quotient plus remainder. Let's convert into formula for two integers. For two integers a comma b, for two integers a comma b, dividend and divisor respectively. There exist two whole numbers. Two whole numbers Q and R, quotient and remainder respectively. Quotient and respectively. See, based on this dividend, let's see. A dividend is A, B is divisor. So A equal to B. Quotient is here Q and R respectively, into Q plus R. A equal to BQ plus R, and here 0 less than or equal to R less than B. Here see, remainder is 1. Here R can become 0 or 1, not less than B. Here B is 2, na? So maybe remainders become 0, 1, not 2. This may be 0 or 1 in this condition, not compulsory. So the famous division algorithm formula is A equal to BQ plus R, and R has the condition 0 less than or equal to B. Remember, in this division algorithm formula, three things are important. First one is remainder is always less than what? Remainder is always less than quotient. Remainder is always less than, what is this? Divisor. Remainder is always less than divisor. And the famous formula, A equal to BQ plus R. By using this formula, we solved so many problems in chapter 1.1, exercise 1.1. And the condition is 0 less than or equal to R less than B. Roughly we have to know what is the, if you know divisor and dividend, but what is the condition for R means it should be 0 less than or equal to R less than divisor. Remainder is always less than the divisor. For example, divisor is 2. Maybe chances R will become 0 or 1 but not equal to 2. You concentrate on these 3 points. For final exams, they ask what is the condition for R? What is the division algorithm formula? This condition. Thank you for watching. In next class, we will continue exercise 1.1. Based on this formula, we will solve some problems from chapter 1, real numbers, page number 3. Chapter 1, real numbers. Page number 3. Okay. Find out the Q and R values using A and B values satisfying A equal to BQ plus R. First question is A equal to 13 and B equal to 3. Satisfying what? A equal to BQ plus R. There clearly mentioned A equal to BQ plus R. So here 13 equal to 3Q plus R. So 13 divided by 3, 3 4s are 12, remainder is 1. So Q equal to 4, R equal to 1. This is the quotient, this is the dividend, this is the divisor, this is the remainder. So Q equal to 4, R equal to 1. Using the same method, you can solve remaining all questions. And next, we discuss next theorem, Euclid's division algorithm. What is algorithm? Algorithm means any process. Algorithm, rules. If you want to solve one question, you follow the rules. For example, 1 plus 2 plus 3 plus, you add the 1 plus 1 2, 2 plus 3 5, like that. You do the rules and process one by one. If you want to prepare, for example, if you want to prepare lemon juice, first you take the lemon, cut the lemon, you take the juice, sugar, water, one by one you add. You take the one by one step. That is the algorithm. So algorithm means you are following some rules process steps. That is called algorithm. Here, division algorithm. Division means what? Previously we solved one problem. 13 divided by 3. 3 4 is 12 and remainder is 1. This is the division. So, division algorithm. How to solve the problem using division. So, Euclid's division algorithm is little bit different. What is that? Let's see. Given positive integers a comma b and there exists q and r satisfying condition is what? A equal to bq plus r and 0 less than or equal to r less than b. This is the Euclid's division algorithm. A equal to bq plus r, 0 less than or equal to r less than b. By using this formula, we find the HCF. By using this formula, find HCF. HCF means highest common factor. By using this formula, we find the HCF of those given numbers. So, let's see one example. One example. Find out the HCF of 160. This is the question. Find out the HCF of 160 by using, this is important, by using Euclid's division algorithm. By using division algorithm. This is the question. Find out the HCF of 160 by using Euclid's division algorithm. So, let's start the answer. I am rubbing here. Solution. In this question, 100 greater than 60. So, 100 greater than 60 means, roughly here take 100 divided by 60. 61 is 60, remainder is 40. You continue this one until you get the remainder 0. 40. So, 60. 41. Here, divisor becomes to dividend. Again, this one becomes to dividend. 41 is 40. Remainder 20. Again, divisor becomes to dividend. 22 is here, remainder is 0. So, in steps, by applying Euclid's division algorithm. By using Euclid's algorithm, what? A equal to BQ plus R. Here A is 100. So 100 equal to B 60. 60 into Q is 1 plus remainder is 40. So here remainder is 40. We are finding SCF. SCF means remainder compulsory 0. So since remainder is not equal to 0. So again applying Euclid's division algorithm to 60 and 40. 60 and 40. For 60 and 40, 60 here, see here, 60 equal to 40 into 1. 40 into 1 plus remainder is 20. Here also again remainder is not equal to 0. Since remainder not equal to 0. Again applying. Again applying division, Euclid's division algorithm for which numbers? 40 and 60. 40 and 20. We did already for 60 and 40. And the next one is 40 and 20. So for 40 equal to, see, 40 equal to 20 into 2 na? 20 into 2 plus remainder is 0. Since remainder equal to 0. So HCF of 160 equal to, what is the Q value here? 20. So this is the, what is the divisor here? Last divisor 20 na? Last divisor is the HCF of 160. So 20 is the HCF of 160. By using the same method, you can solve the exercise 1.1 questions and do this problem. Same, for numbers are different here. For example, in do this problem for 30 and 20, you apply here. 30 is here, 20 is here. Same problem you continue. This is the by applying Euclid's division algorithm. You can solve exercise 1.1 first questions, all problems, and do these problems also. If you have any doubt in this, you can comment. Thank you. If you like this example 2, let's see the question. Show that any positive odd integer is of the form of 4q plus 1 or 4q plus 3. For any positive odd integer is in the form of this form. So, solution. By Euclid's division lemma or Euclid's division formula, what? A equal to BQ plus R. R value is 0 less than or equal to R less than B. Is in the form. Here clearly mentioning 4q plus 1. In place of b, 4. So, let assume any positive odd integer na? Let some integer a and b, here b equal to what? 4. Substitute in a in this formula, a equal to 4q in this in this formula 4q plus r. We have to show 4q plus 1, 4q plus 3. So a equal to 4q plus r. Here r conditions are 0 less than or equal to r less than b value is 4. So, r equal to 0, r 1, r 2, r 3. Substitute if r equal to 0. That implies a equal to 4q plus 0. 4q plus 0 means equal to 4q. 4q means this is the 4 and for some any integer q value it will become even. So this is even. If r equal to 1, a equal to 4q plus 1. Plus 1 means for any number we are adding extra 1. It will become odd. Odd. This is the odd. And if r equal to 2, a equal to 4q plus r value is 2. If you take the 2 common, here 2q plus 1. Any number, if you multiply with 2, it will become even. So this one also even. If r equal to 3, a equal to 4q plus 3. 4q plus 3 means for any number. For example, you take 1. You are adding here 3. 1 plus 3. It will become what? Any odd number you are adding to any number. Here take 4q plus 2 plus 1. 2, you take the 2q plus 1 and again here is 1. And here again adding 1. Means this is also odd. So show that any positive odd integer is odd integer. 1 is odd, here 3 is odd. For odd integer is form of the 4q plus 1 or 4q plus 3. Here we got the what is the form? 4q plus 1 and 4q plus 3. So for any odd integer, the form of the numbers are 4q plus 1 or 4q plus 3. So therefore every positive odd integer, for every positive odd integer is of the form of the form of 4q plus 1 or 4q plus 3. Hence proved. In the same process, you can solve exercise 1.1 second sum. There is the question is here, in place of 4q plus 1, in place of 4q plus 3, 6q plus 3, 6q plus 5. Same method you can use. Solve the 6q plus 3, 6q plus 5. This is the second sum in exercise 1.1. Same methods. Here you take b value 6. So b value 6 means you get the r value from 0 to 5. You can solve. And next question is exercise 1.1 third question. Use Euclid's lemma to show that the square of any positive integer is of the form of 3p plus 1. So, solution. By Euclid's division lemma, A equal to BQ plus R and 0 less than or equal to R less than B. Here B value is 3. 3p and 3p plus 1 in the form of, so let a integer A and B equal to here 3p. B equal to, from formula A equal to 3q plus R and B is the 3 na, so 0 less than or equal to R less than 3. R values become 0 R, 1 R, 2. 0, 1, 2. If, see, if R equal to 0, that implies A equal to 3q plus 0. So, equal to 3q. And here mentioning the square of any positive integer. Square of any positive integer means square of A square equal to 3q square. 3 square means 9q square. 9q square. Here you take 3 into 3q square. You can write. So here 3. Let's P. Where P equal to 3q square. So, A square equal to 3p. The square of any positive integer is of the form of 3p. And next, if R equal to 1, that implies A equal to 3q plus 1. That implies A square equal to 3q plus 1 whole square. A plus B whole square formula na? Here becomes 3q 9 square means 9q square plus 2 into 3q into 1 and 1 square means 1. So here 9q square plus 6q plus 1. 2 3 is the 6, na? 6q plus 1. So here you take 3 common. 9, you can write na 3 3 is the 9. So here 3q square plus 2q plus 1. So here also same again. Let's take this total value is p. 3p plus 1, where p equal to 3q square plus 2q. In this condition also, the square of any positive integer is in the form of 3p plus 1. In the form of 3p plus 1. Next, one last condition is r equal to 2. See here. If r equal to 2, so a equal to 3q plus 2. Square na? Square of the. So a square equal to 3q plus 2 whole square. A plus b whole square. 3q square. A square plus b square plus 2ab na? So 9q square plus 2 into 3q into 2 plus 2 square means 4. 9q square plus 12q, yes, 2 3 is the 6, 6 2 is the 12 plus 4. Here 9q square plus 12q, you can write 3 plus 1. For 4 you can write 3 plus 1. 3 plus 1 also 4 na? For simplifying, here you can take from these 3 terms, common is 3. 3q square, right now 3 3 is the 9 square, and here 3 common means 3 4, and here is the 1, and again 1. So square of the any positive integer is in the form of 3p or 3p plus 1. Here again you take p value, where here you have to write where p equal to this value. Here is p value different, here also different, this one, this one. We are choosing their p value is 4q plus 1. Therefore, hence by using Euclid's division lemma, the square of any positive integer is of the form of 3p plus 1. If you like the video, you can share and subscribe. In next class, we discuss about the fundamental theorem of algorithm. Thank you. Fundamental theorem of arithmetic. Today's topic is fundamental theorem of arithmetic. First, we say what is the statement. After that, we discuss what is that. Every composite number can be expressed or factorized as a product of primes, and this factorization is unique apart from the order in which the prime factor occurs. Now it's looking difficult. We discuss first. Every composite number. Every composite number means, what is the composite number? First, what is composite number? The number which has more than 2 factors is called composite number. composite numbers are start from 4. The number which has more than 2 factors. So composite numbers are start from 4. 4, 6, 8, 9, 10. See, composite 4 factors are what? 1 for the 1 and 2 to the 4, 4 1 the 4. So 4 factors are 1, 2, 4. So the number which has more than 2 factors is called composite number. So every composite number can be expressed, means factor. These are factors na? Can be expressed or factorized anywhere as a product of primes. For example, for 4, 1 into 4 you can write. 1 into 2 into 2. You can write this na? Product of primes. 2 is the prime number. 1 is the prime number. And this factorization is unique. Unique means you write the 4 equal to 2 into 2 into 1. And for 6 you write the 2 into 3 for one person. For 6 equal to 6 factors are 2 into 3 na? For example, A person write 2 into 3 and next B person he can write 3 into 2. Both are equal na? 2 into 3 equal to 6, 3 into 2 equal to 6. So this factorization is unique. Both are unique. Apart from the order in which the prime factors occur. Order are different. First you wrote the 2 is the first. Here he wrote 3 is the first. You can write any method. 2 into 3 or 3 into 2. Main one is this factorization is unique. So every composite number can be expressed as a product of prime. 2 into 3. After that 8 you can write 2 2 is 4. 4 into 2. Product of primes. And this factorization is unique. Anyone write in any method. 2 into 3, 3 into 2. Numbers are the same. Unique. Apart from the order in which the prime factor. This is called fundamental theorem of arithmetic. By using this method, which exercise? Exercise 1.2 you can solve all problems. I will solve one problem for you. Which exercise? By using method exercise 1.2. This is the in first sum 140. By using fundamental theorem of arithmetic, you write the product of prime factors. So how to write? 140. Okay. 2 sevens are 14. 0. And again 2 threes are 6. Meaning 5. And next here 5 table. 5 sevens are. Okay. These are all prime numbers na? Every composite number can be expressed as a product of primes. These all are primes. And this factorization is unique. If you do, you get the same numbers. For example, for example, I started with 2 number. Another person starts with 7 number. 7 twos are 7. And 2 tens are. And 2 fives are. See? numbers are numbers in different way. First I used 2 number. This person used first 7 number. That using is different. But numbers are same na? 7, 5. Here 7, 5. 2, 2. If you do any method, you get the same answer. So this factorization is unique. Apart from the order in which the prime factor occur. So 2 into 2 into 5 into 7. This is the first question. In this this is the first one. In this maybe four problems are there. You can solve by using the same method. And next one. And the next question is from page number 8, example 3. Consider the number of the form 4 power n. Number of the form is 4 power n, where n is a natural number. Check whether there is any value of n for which ends with 0. First we understand what is the question. Natural number. Natural number means it starts from 1, 2, 3, 4, 5, 6. Okay? Natural numbers. The number of the form 4 power solution 4 power n, where n is a natural number. Check whether there is any value of n. If you substitute n value 1, 2, 3, 4, 5, that one for which ends with 0. If you substitute n value natural number, it will ends with 0. Which ends with 0. With ends with 0 means what is the numbers? 10, 20. The numbers become 10, 20, 30, 40. Is it correct? So, okay, these are the numbers. So, ends with the 0. Is in the form of 4 power n, where n is a natural number. Check whether there is any value of n ends with 0. So 10 means 2 5s. So for any number ends with 0 means factors are 2 5. For 20 we check. For 20, 2 10s and 2 5s. And again for 30, 2 1s, 2 5s. And again 3 5s. Yes? So in this, what is the common? The number which ends with 0 has the factors 2 5. 2 5. 2 5 is the common factors. 2 5 are common factors. So the number of form 4 power n, where n is a natural number, is the value of for n which ends with 0. We have to check. So if a number ends with 0 means it should be divisible by 2 and 5. Yes, ma? If a number ends with the digit, digit 0. Ends with the 0 means it should be it should be divisible by 2 and 5. 2 and 5. The number is the form of number is 4 power n. So 4 power n equal to, you write 2 into 2 power n. In this, what is the factors? 2 factor. 5 is not a factor. So that is 5 is not a factor. 5 is not a factor of 4 power n. This number is divisible by 2, not divisible by 5. So hence 4 power n is not divisible by, is not divisible by 5. It is not divisible by 5. 4 power n cannot be n with the digit 0 for any natural number. For any natural number. Once again, any natural number. Using the same method, you can solve the exercise 1.2. Which problem? Third sum. Here 6 power n. Same problem. Here is the 4. In that question 6 power n. 6 power n for any natural number ends with 0. That is we have to prove that. Here 6 means you write the 2 into 3. 2 into 3 means it is not divisible by 5. Only divisible by 2. It is not satisfied this again condition. If that number ends with 0 means it should be divisible by 2 and 5 factors. That is the common. So here also 6 power n cannot be n with the digit 0 for any natural number. Yes. And the next question is page number 8, example 4. Find the HCF and LCM of 12 and 18 by the prime factorization method. Here what is HCF and what is LCM? So HCF, product of the smallest power of each common prime factors of the given numbers. 12 and 18 are given numbers. And LCM, product of the greatest. In HCF, smallest. In LCM, greatest. Power of each prime factors of the given numbers. Here is the common prime factors. Here is the every prime factor. So, for 12, how can we write? 2 6 and 2 3. Yes, 2 into 3. For next number is 18. For 18, 2 9s and 3 3s. Yes, 2 3 and 3. So First one is HCF. In HCF, you remember common. The product of the smallest power of each common factors. In this, what are the each common factors? 2 is the common factor and 3. In both, we have 2 and 3. So, 2, 3 is confirmed. 2 into 3. And one more thing is common prime factors of power of each smallest power. So, here 2 is 2 times. Here 2 is 1 time. So, smallest power means this is the 1 time. This is the 2 times. So, here you take only 1 time. 2 power 1. And again 3 is here 1 time. Here 3 is 2 times. So, smallest power means only you take 1 time. 2, 3 is 6. That is one method. And one more method, na? You directly take, you first of all you do the prime factors. 12 equal to 2, 2, 2 and 3. And for 18, 2, 2, 3 is and 3, 3 is. Common factor, na? In this is the common. So put it. And in this, common. You don't have one more chance. So you take only 1 time. Smallest means only you take 1 time. And one more thing is common. Common means in both you should be number is there. So 2, 3. You take 1 time 2, 1 time 3. This is the SCF. For LCM, na, this is the different. For LCM, you remove circle here. These are the factors. Okay. You take every factor, product of the greatest power of each prime factor. 2 is the factor. What is the highest factor in this? 2 square. 2 times it will come 2 times. 2 times means 2 square, na? 2 square into 3. Here 2 into 3 square. So, greatest power of each prime factors. 2 is the prime factor. Greatest. So, 2 square. And in this, 3 square. Greatest of the each prime factors of the numbers. So, 2 square means 4. 3 square means 9. 3 nines are 36. So, for HCF is 6, LCM is 36. Using this one, you can solve exercise 1.2 all questions. Second sum. In second sum, exercise 1.2 all questions. Using the same. First you factorize with prime factorization. Not normal, prime factorization. After that, for SCF, you take the common factors. For LCM, you have to take every prime factor and greatest one. Here, na, common one only and least one. Least one means smallest one. Smallest one. Okay. For example, one more we take. One more example. I am rubbing this one. For example, not from the textbook, I am taking 12, 18 and one more thing is 14. So, find out the SCF. SCF means 12 equal to 2 6 2 3 for this. So, 12 equal to 2 into 2 into 3. For 18, 2 nines and 3 threes. So 2 into 3 into 3. For 14, 2 sevens. See, that's why I am explaining this question. 2 sevens. So, what is SCF? Tell me. Product of the smallest power of each common. In this 3, what is the common? Only 2. So 2. Smallest power. So only 1. In this 3, one more thing is we don't have. So SCF is 2. Product of the smallest power of each common prime factors of the given numbers. There is no common other than 2. In this we have only 2. In this we don't have. Another one. LCM. LCM equal to product of greatest power of each prime factors. Here you take 2 or how many times? 2 square. So 2 square. What is the compulsory? You take all prime factors. 2, 3, 7 are common. In this 2 is 1 time. 7 is 1 time. Here 2 is 1 time. Here 2 is 3 times. 2 into 3 square. Here 2 square into 3. So highest to power na. So 2 square. Here 3 square. 2 square means 4 into 9 into 7. So final answer is 36 into 7. So 252 is the LCM. SCF is 2. Okay. Using this, you can solve from exercise 1.2 second sum all questions. If you like this video, you share and subscribe. Thank you for watching. Real numbers, exercise 1.2, fourth question. Explain 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 3 into 2 into 1 plus 5 are composite numbers. Already we discussed what is composite number. The number which has more than 2 factors is called composite number. So here we have to explain these 2 are composite numbers. Solution. What are the terms? 7 into 11 into 13 plus 13. In mathematical, in algorithm, what are terms? Term means that with positive and negative. Positive and negative. Means with addition, with subtraction, we separate the terms. Separate the numbers. That is called term. See here, 7 into 11 into 13 and here is the plus. So, this total is called one term. And this one is called one term. Here how many terms? This is 1 and this is 2. These 2 are terms in mathematical. So, we have to explain these 2 numbers are composite numbers. Composite numbers means the numbers have the more than 2 factors is called composite numbers. So, this 7 into 11 into 13, this is one term plus this is one term. Okay. See, in these 2 we can take 13 is the common. So 13. 7 into 11 into here 13 is the common into 1. Yes, into 1 plus total, this is the common. We are taking 13 is the common plus 13. Yes, in this we took the 13 common. Sorry, here what will come? 13 is the common, na? So here 1 will come. Next 13. So here 7 into 11, 77. 77 into 1, 77. So 77 plus 1. 13 into 77 plus 1 means 78. We can factorize here 78. 2 3s are 2 9s are and 3 1s are 3 3s are. So from finally 13 into 2 into 3 into 30. This number is converted into factors of primes. Factors of prime means that number is composite number. So 7 into 11 into 13 plus 13 became 13 into 2 into 3 into 30. This equal to became factors of primes. Factors of prime means that number is composite number. So we proved this number is composite. Similarly, this number. See, I am rubbing here this one. And the second number is what? 7 into 6 into 5 into 3 into 2 into 1 plus 5. See, step by step. This is term 1. This is term 2. Term means that numbers are separated by with plus or minus. Here plus separated 2 terms. In these two we can take 5 is the common. So 5. 5 into 7 into 6 into 5 is we took the common. 3 into 2 plus 1. Yes? Again 5 become here plus 5. 5 into 7 6 42. 42 into 3. 42 into 3, 3 2s are 6, 3 4s are 12 and again 2. 2 6 are 12, 2 2 4s are 4, 1 5, 252. Here answer is 252 plus again here 1. So 5 into 253. Yes? And we so finally 5 into 253. So this number also composite number. We factorized primes of factors. That number is converted into factors of primes. So 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 3 into 2 into 1 plus 5 are composite numbers. Hence proved. Hence proved. Okay, this is the fourth question. And the next question is what? From the same exercise, fifth question. Fifth question you can solve. From exercise 1.2, fifth question you can try it. Okay. Next one is Same exercise, sixth question. What is the last digit? What is the last digit of 6 power 100? What is the last digit of 6 power 100? 6 power 100 means, first we check. For example, 6 power 1. What will come? 6 power 1 means 6. Yes. And 6 power 2 means 6 is the 36. 6 power 3 means 36. 6 again 3 times na? 2 times is 36. One more time. 6 is the 36. And 18. 18 plus 216. So, if you take 6 power 1, 6 square, 6 cube, 6 power 4, any one, the last term is 6. For any, therefore, for any natural number n, 6 power n, for 6 power n, the last digit is of 6 power n is 6. So, here what is the question? What is the last digit of 6 power 100? So, the last digit of 6 power 100 is, what will come? N is natural number. So, for any power, the last digit is 6. So, this is the exercise 1.2, sixth one. Okay? And the next. So, exercise 1.2 is finished. In next classes, we discuss part 2. Some all theorems and exercise 1.3 and exercise 1.4. So, from up to these videos, you finish exercise 1.1, exercise 1.2 and all theorems. In next video, we will discuss exercise 1.3, 1.4 and all next coming theorems. If you like this video, please share and subscribe. Thank you.